Tonight, we're going to confront one of the deepest mysteries in all of physics. Imagine you have an electron. You measure its position and find it at one precise point. Simple enough. But here's the question that has haunted the greatest minds for over a century. Where was that electron the instant before you looked? Your gut says it must have been right there, sitting in that spot, waiting to be found. But quantum mechanics, the most accurate theory humans have ever built, says something far stranger. It says the question might not even have an answer. The electron may not have been anywhere in particular. Not hidden, not too small to see, but genuinely without a single definite location. And tonight, you're going to understand exactly why. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you probably take for granted. The idea that objects have locations. Right now, you're somewhere. Maybe you're in your bedroom. Maybe you're on a bus. Maybe you're sitting outside somewhere, staring up at the night sky. Wherever you are, you're in a specific place. If someone called you right now and asked where you are, you could give them a definite answer. You're here and not there. You're in this room and not the room next door. You're in this city and not some other city across the world. This seems completely obvious. So obvious that it barely feels worth saying. Of course things have positions. Of course objects exist in definite places. A rock sitting on a hillside is at one particular spot on that hillside. It's not at two spots. It's not blurred between three possible locations. It's right there. You can walk over to it, put your hand on it, and confirm exactly where it is. Your car is in the driveway or in the parking lot or wherever you left it. The moon right now is roughly 384,000 kilometers from Earth, tracing a path through space that we can predict with extraordinary accuracy for centuries into the future. These objects all have definite, specific locations, and they have those locations whether or not anyone is watching them. This is how the everyday world works. Objects exist in definite places. They follow definite paths. If you throw a baseball, that baseball traces a smooth arc through the air. At every single instant during its flight, the ball occupies one specific point in space. It doesn't smear across the stadium. It doesn't flicker between locations. It moves from one definite position to the next, along a trajectory determined by its speed, its angle, the pull of gravity, and the resistance of air. You can describe exactly where that ball is at any moment using the equations Isaac Newton wrote down more than 300 years ago. And here's the critical point. The ball has that definite position whether or not you're watching it. If you close your eyes while someone throws a baseball across a field, the ball doesn't stop having a location. It doesn't become smeared out or undefined just because nobody happens to be looking. The ball is still at one specific point, following one specific path. Your ignorance about where it is doesn't change where it actually is. The universe doesn't need your attention in order to have a definite configuration. Let me give you another example that makes this contrast even sharper, because this example is going to become very important later. Imagine someone flips a coin and catches it, covering the coin with their hand before you can see the result. You don't know whether it's heads or tails. There's a 50% chance of each. But here's the thing. The coin is definitely one or the other. It's not somehow both at the same time. It's not in some undefined state waiting for you to look before it decides what to be. It is already heads, or it's already tails. You simply don't know which. When you finally lift the person's hand and see that the coin landed on heads, you haven't caused it to become heads. You've simply learned what it already was. The coin had a definite state the entire time. Your act of looking didn't create the outcome. It only revealed it. This kind of uncertainty, the kind you deal with every single day, is what physicists call classical uncertainty. It's uncertainty that arises purely from a lack of information. The reality is already settled. You just don't have access to the answer yet. Think of it like a sealed envelope containing a letter. The words written on the letter are already there. They exist on the paper inside, whether you've opened the envelope or not. Opening the envelope doesn't create the words, it just reveals them. This seems like common sense because it is common sense. It's the way the world appears to work at every scale you've ever experienced. Objects have definite properties. Those properties exist independently of whether anyone knows about them. The universe carries on just fine without anyone watching. Now, hold that picture firmly in your mind, because we're about to watch it come apart. In the early 20th century, physicists started studying the behavior of very small things: atoms, electrons, individual particles of light, known as photons. And what they discovered didn't just surprise them. It shattered the classical picture so thoroughly that the greatest scientific minds of the century spent decades arguing about what it meant. Many of them never stopped arguing until the day they died. Here's what they found. When you zoom down to the scale of atoms, roughly 1/10,000,000th of a meter, the familiar rules change, not subtly, not in some minor technical way that only matters for specialists working in laboratories. The rules change fundamentally. The basic assumption you and I just discussed, that objects always have definite positions, that assumption appears to break down. Not because our instruments are too clumsy to see where the electron is. Not because it's moving too fast to track, but because according to the mathematics of quantum mechanics, the most precise and thoroughly tested theory in the history of science, the electron may not have a single definite position to find. Let me be very precise about this because it's the heart of everything we're going to explore tonight. In classical physics, when you don't know where something is, the object is still somewhere specific. You just need better instruments or better data to learn its location. The object has a definite position. Your uncertainty is about your knowledge, not about reality. In quantum mechanics, the situation appears to be fundamentally different. The theory doesn't say the electron is sitting at some particular location, and we simply haven't figured out which one. It says the electron is described by a mathematical entity called a wavefunction, and that wavefunction typically does not single out one definite position at all. The wavefunction is the central mathematical object of quantum mechanics. It's the thing that contains everything there is to know about a quantum system. Every electron has a wavefunction. Every atom has one. Every molecule, every photon, every quantum system you can name has a wavefunction. If you want to predict anything about a quantum system, anything about where a particle might be found or how it might behave, you begin with its wavefunction. So what exactly is a wavefunction? At its most basic, a position wavefunction for an electron is a mathematical function that assigns a value to every possible location in space. But the value it assigns isn't an ordinary number. It's a special kind of number called a probability amplitude. And probability amplitudes are genuinely different from ordinary probabilities. Understanding this difference is the key to understanding why quantum mechanics is so strange. And I'm going to take my time explaining it because if you grasp this one idea, you'll understand something that most people, even many people who believe they understand quantum mechanics, consistently get wrong. An ordinary probability is a simple number between 0 and 1 that tells you how likely something is. If there's a 50% chance of rain tomorrow, the probability of rain is 0.5. If you roll a fair die, the probability of landing on any particular face is 1 in 6. Ordinary probabilities are straightforward. They add up in a simple way. If there's a 30% chance of event A and a 20% chance of event B, and those events can't both happen, then there's a 50% chance that one of them happens. You just add the probabilities. This is how classical probability works. It's intuitive. It matches our everyday experience. Probability amplitudes don't work this way. A probability amplitude can be positive or negative, and it can even be what mathematicians call a complex number, a number involving the square root of -1. You don't need to know the mathematics to understand the consequence. What matters is this: because probability amplitudes can be positive and negative, they can cancel each other out. Two amplitudes corresponding to two different ways something could happen can combine and give 0, even though neither amplitude was 0 on its own. This is exactly like how waves work. If you've ever watched two waves on the surface of a lake meet each other, you've seen interference. When the peak of one wave aligns with the peak of another, they combine and you get a bigger wave. That's constructive interference. But when the peak of one wave aligns with the trough of another wave of the same height, they cancel. The water goes flat. That's destructive interference. The waves don't disappear. They're still there, still carrying energy. But at that specific point, they cancel each other out perfectly. Probability amplitudes do exactly the same thing. Two quantum paths leading to the same outcome can interfere. They can reinforce each other, making the outcome more likely. Or they can cancel each other, making the outcome less likely, even making it impossible. This interference between probability amplitudes is the single most important feature of quantum mechanics. It's what makes quantum probability fundamentally different from classical probability, and it's the source of nearly everything that seems bizarre about the quantum world. In 1926, a physicist named Max Born figured out the precise rule connecting probability amplitudes to actual experimental results. The rule is beautiful in its simplicity. If you want to know the probability of finding an electron at a particular location when you measure its position, you take the probability amplitude the wave function assigns to that location, and you square its absolute value. The result is always a positive number between 0 and 1, and it gives you the probability of detecting the electron there. This is called the Born rule, and it's one of the foundational pillars of quantum mechanics. Every prediction the theory makes about measurement outcomes comes through this rule. You start with the wave function. You extract the amplitude for the outcome you're interested in. You square it, and you get the probability. Experiments confirm these probabilities with extraordinary precision. Quantum mechanics has been tested to better than 10 decimal places in certain experiments. No other theory in the history of science has been tested so rigorously and passed every single test. Now, there's a very common misconception that I want to confront directly. Many people picture the wave function as a kind of blurry photograph of the electron. They imagine the electron as a tiny ball that's somehow been smeared out across space, like fog spreading across a valley, thinning as it spreads. This picture is wrong. The wave function is not showing you a smeared out electron. The electron is not literally spread across space the way butter spreads on toast. It's not a cloud of matter getting thinner and thinner as you move away from the center. What the wave function is, at its core, is a mathematical description of the quantum state. It tells you where the electron might be detected if you perform a position measurement, and it tells you the probability amplitudes associated with each possible location. The wave function is a description of possibilities, weighted by amplitudes that can interfere with each other. It's not a description of a physical substance smeared across space. Here's an analogy that might help. Imagine a weather forecast that tells you the probability of rain for every neighborhood in your city. Maybe downtown has a 90% chance, the suburbs have a 40% chance, the outskirts have a 5% chance. This forecast doesn't mean that rain is physically spread across the entire city like a thin mist everywhere at once. It means that if you go to a particular spot and check, you'll either find rain or you won't, and the forecast tells you how likely each outcome is for each location. The wave function is somewhat like this probability map, but with a crucial difference. The weather forecast reflects your ignorance about where rain will actually develop. Somewhere in the atmosphere, physical processes are unfolding that will determine exactly where it rains. The rain has a definite physical cause that you simply can't track perfectly. The wave function, as far as most formulations of quantum mechanics are concerned, isn't reflecting ignorance about some hidden, definite reality underneath. It may be the most complete description of the electron that nature allows. And this is where the true strangeness begins. Let me bring it into focus with a concrete example. Imagine you have an electron confined inside a tiny box, roughly 1 nanometer across, about the width of a small molecule. Quantum mechanics tells you the electron's wave function inside this box looks like a wave. It has peaks where the amplitude is large and nodes where the amplitude is exactly 0. If you measure the electron's position, you find it at one specific point inside the box, not spread across the box, not at multiple locations simultaneously. One precise point. But here's what happens when you repeat the experiment. You prepare the electron in exactly the same quantum state, over and over, and each time you measure its position. Each individual measurement gives you one definite location, but the location changes from trial to trial, appearing random. After thousands of repetitions, however, a clear pattern emerges. The distribution of measured positions matches the squared amplitude of the wave function precisely. In regions where the wave function has large amplitude, you find the electron frequently. In regions where the amplitude is small, you find it rarely. And at the nodes, where the wave function's amplitude is exactly 0, you never find the electron. Not once in 10,000 trials. Not once in a million. Never. This last fact is especially revealing. There are specific locations inside the box where the probability of finding the electron is precisely 0. If the electron were really a tiny classical ball, bouncing around inside the box, rattling off the walls the way a billiard ball bounces inside a pool table, you'd eventually expect to find it everywhere. There'd be no reason for certain spots to be permanently off limits. But the wave function has nodes, locations where its amplitude vanishes, and the electron is genuinely never detected at those points. This is a direct, measurable consequence of the wave nature of the quantum state. It has no explanation in classical physics. Nothing in the classical world behaves this way. So let me bring all of this back to the central question we started with. Where is the electron before you measure it? If we take the standard mathematical framework of quantum mechanics at face value, the answer is genuinely startling. Before you measure its position, the electron doesn't generally have one. It has a wave function that assigns probability amplitudes across many possible locations, but no single location is singled out as the real one. The electron isn't hiding at a specific point the way a coin is hiding a definite face under someone's hand. The wave function, spread out across space with all its peaks and nodes and interference possibilities, may be all there is to say about the electron situation. And this is not a statement about human limitations. It's not that we need better instruments. It's not that we need faster computers or cleverer experimenters. The claim goes deeper. According to quantum mechanics, before a position measurement occurs, there may be no fact of the matter about where the electron is. The universe itself may not have assigned it a location. Go back one final time to that flipped coin. The coin has a definite result, heads or tails, that you simply haven't seen yet. Your uncertainty is about what you know, not about what the coin is doing. The electron situation is fundamentally different. Its uncertainty may not reflect your ignorance at all. It may reflect the actual state of nature. The position may be genuinely undefined, not merely unknown. This distinction between uncertainty born from ignorance and uncertainty that may be woven into reality itself is the most important idea in all of quantum mechanics. It's the reason the theory is strange. It's the reason brilliant physicists have debated its meaning for over a century. And it's the starting point for everything we're going to explore next. Because if the electron doesn't have a definite position before measurement, then what happens when two possible paths through space are available to it? What happens when the wave function passes through two openings at the same time? This brings us to the most famous experiment in quantum physics, the double-slit experiment. And what it reveals is even more striking than what we've discussed so far, because it shows that these probability amplitudes aren't merely abstract mathematical tools. They have real, physical, visible consequences. They interfere, and the interference patterns they create are flatly impossible if the electron is secretly traveling along one definite classical path. To understand what's really happening with an electron before you measure it, we need to look at an experiment, not a thought experiment, not an analogy, a real physical experiment that anyone with the right equipment can perform today, and that has been performed thousands of times over the past century with the same result every single time. This experiment is so important that the physicist Richard Feynman once called it the only mystery of quantum mechanics. He said that if you could understand this single experiment, you would understand everything that is strange about the quantum world. He wasn't exaggerating. The experiment is the double-slit experiment, and what it reveals about the electron's behavior before measurement is so striking that it essentially forces us to abandon the classical picture of reality. Let me set up the experiment, and I'm going to go slowly, step by step, because each detail matters. Imagine a wall with two narrow slits cut into it, side by side, separated by a tiny gap. Behind the wall is a detector screen a surface that records wherever a particle hits it. You can think of this screen as being coated in something that registers an impact. Every time a particle arrives, a small dot appears on the screen marking the exact spot where it landed. Over time, as many particles arrive, the dots build up into a pattern. The pattern tells you where particles tend to land and where they don't. Now, before we send electrons through this setup, let's think about what would happen if you used ordinary objects instead. Imagine throwing tiny marbles at the wall. If only the left slit is open, the marbles that make it through will cluster behind the left slit. You'll see a band of impacts directly behind that opening. If only the right slit is open, you get a band behind the right slit. If both slits are open at the same time, the pattern on the screen is simply the combination of those two individual bands. It adds up. Some marbles go through the left slit and land behind it. Some go through the right slit and land behind it. The two bands might overlap a little in the middle, creating a slightly brighter region there, but the overall pattern is just the sum of the two single slit patterns. This is exactly what classical physics predicts. Every marble goes through one slit or the other, following one definite path, and the combined pattern is just the two individual patterns laid on top of each other. Now, replace the marbles with light. If you shine a beam of light at the double slit, something very different happens. Instead of two bright bands on the screen, you see an interference pattern. A series of bright and dark stripes stretching across the detector surface. Bright, dark, bright, dark, bright, dark, alternating in a regular rhythm. The bright stripes are where light waves from the two slits arrive in sync, their peaks aligning to reinforce each other. Constructive interference. The dark stripes are where light waves from the two slits arrive exactly out of step. One wave's peak meeting the other wave's trough, and they cancel. Destructive interference. The light goes dark at those locations, not because no light is reaching them, but because two waves are cancelling each other perfectly. This was first demonstrated by Thomas Young in 1803, and it was considered definitive proof that light is a wave, because only waves interfere. Particles, at least classical particles like marbles, don't. Particles go through one slit or the other. Waves pass through both and their amplitudes add together, producing interference. This distinction between particle behavior and wave behavior seemed clear for over a century. Particles do one thing, waves do another. The two categories are separate and well defined. Then, in the 20th century, physicists started sending electrons through double slits, and what happened demolished the clean boundary between particles and waves. Let me describe the electron version carefully. You set up the double slit the same way. Two narrow openings in a barrier, a detector screen behind them. Now you fire electrons at the wall, but here's the crucial detail. You fire them one at a time, one single electron, then a pause, then another single electron, then another. There is never more than one electron in the apparatus at any given moment. This eliminates any possibility that electrons are somehow bumping into each other, or collectively creating a pattern through interactions between multiple particles. Each electron is alone. Each electron makes its journey from the source to the barrier to the screen entirely by itself. When a single electron arrives at the screen, it produces a single dot at one specific location. Not a smear, not a blur, not a pattern. One dot. One point of impact. In this sense, the electron behaves exactly like a particle. It arrives at one spot and nowhere else. If you watch just a handful of electrons arrive, you'd see a scattering of dots that appears completely random. One here, one there, another over here. No pattern, no structure, just random points of impact scattered across the screen. You'd think you were watching tiny marbles. But here's what happens when you send many electrons through, one at a time, and let the dots accumulate. After hundreds of electrons, a faint pattern starts to appear. After thousands, it becomes unmistakable. After tens of thousands, it is crystal clear. The dots form an interference pattern, bright bands where many electrons land, dark bands where almost none land, alternating stripes stretching across the screen, identical in structure to the interference pattern produced by a beam of light. This result was first confirmed experimentally in 1927 by Clinton Davison and Lester Germer, who showed that electrons exhibit wave-like behavior when scattered from a crystal surface. G.P. Thomson independently demonstrated electron diffraction around the same time. And in 1989, a team led by Aki-Ra Tonomu-Ra at Hitachi performed the iconic version of this experiment, sending individual electrons through a double-slit apparatus one at a time and watching the interference pattern build up dot by dot. The results were undeniable. Individual electrons arriving alone, one by one, each landing as a single point, collectively produce an interference pattern. Let me take you through what this experiment actually looks like as it unfolds, because the experience of watching it is almost as important as the result. In the first few seconds, the screen is nearly blank. A dot appears, then another, somewhere completely different, then a third, in what seems like a random location bearing no relation to the first two. If you were watching in real time, you'd see nothing but scattered noise, random points of impact with no discernible structure. You'd have no reason to suspect anything unusual was happening. It would look exactly like what you'd expect if someone were throwing tiny marbles at random locations on a wall. After a few dozen electrons, you might start to squint at the screen. Is there a pattern forming? Probably not. The dots are still sparse enough that your brain can't pick out anything meaningful from the randomness. It still looks like noise, just scattered points distributed haphazardly across the detector surface. But after several hundred electrons have arrived, something begins to emerge. Faintly, almost imperceptibly, certain regions of the screen are accumulating more dots than others. There are hints of vertical stripes beginning to form, but it's subtle. You're not sure if you're seeing a real pattern or just imagining one, the way you sometimes see shapes in clouds. After 1,000 electrons, the pattern is unmistakable. Clear bands are forming, bright stripes where dots cluster densely, dark stripes where almost no dots appear. The spacing is regular. The structure is precise. After 10,000 electrons, the interference pattern is as sharp and clean as anything produced by a beam of light, passing through a double slit. Alternating bright and dark bands stretching across the screen in perfect mathematical order. And here's what makes this so extraordinary. Every single one of those 10,000 electrons arrived alone. Each one made the journey from source to barrier to screen entirely by itself. There was never more than one electron in the apparatus at any given moment. Each one landed as a single, random dot, giving no indication of the grand pattern it was contributing to. And yet, collectively, as if coordinated by some unseen conductor, they assembled themselves into an interference pattern. A pattern that requires wave-like behavior. A pattern that requires something to have passed through both slits simultaneously. A pattern built by 10,000 individual particles, each of which arrived at one precise point, each apparently knowing nothing about where the others had landed, and yet together producing a result that no collection of classical particles could ever produce. This is not a theoretical prediction waiting for confirmation. This is a direct experimental observation, recorded on camera, repeated in laboratories around the world. The footage from the Hitachi experiment, showing the pattern building up dot by dot, is one of the most striking pieces of scientific evidence ever captured. It doesn't just suggest that something strange is happening at the quantum level. It shows it, directly and undeniably, one electron at a time. Stop and think about what this means. Because if you don't find this disturbing, you haven't understood it yet. Each electron arrives as a particle, one dot, one location. But the distribution of those individual dots, the collective pattern they form over many arrivals, is an interference pattern. And interference is something only waves do. It requires something to pass through both slits simultaneously and combine on the other side. Waves do this naturally. A water wave hitting a barrier with two openings splits and passes through both. The two resulting waves overlapping and interfering beyond the barrier. But how can a single electron, which arrives as a single dot at a single point, be passing through both slits? You might think the answer is simple. Maybe the electron goes through one slit and its wave function somehow goes through both, and the math just works out. But that doesn't explain the dark bands. In the dark regions of the interference pattern, electrons almost never arrive. Zero impacts, or close to it. If each electron was simply going through one slit or the other, the pattern should look like the marble pattern. Two overlapping bands, no dark stripes, no interference. The fact that there are locations on the screen where electrons never land, locations that would receive plenty of impacts if only one slit were open, means something is cancelling the probability of the electron arriving there. Something passing through the left slit is interfering with something passing through the right slit, and the interference is destructive at those dark bands. The probability amplitudes from the two paths are cancelling, and here is the key. This cancellation happens even when only one electron is in the apparatus at a time. The electron isn't interfering with other electrons, it's interfering with itself. Or more precisely, the probability amplitudes associated with the electron passing through the left slit and the right slit are interfering with each other, producing a pattern that cannot be explained if the electron took only one path. Let me make this as concrete as possible. Suppose you close the right slit and leave only the left slit open. You fire thousands of electrons through, one at a time. You record where they land. You get a band behind the left slit. A smooth distribution centered on the left opening. Nothing unusual. Now close the left slit and open only the right. Fire thousands of electrons. You get a band behind the right slit. Again, nothing unusual. Now open both slits and fire thousands of electrons, one at a time. If each electron simply went through one slit or the other, you'd expect the pattern to be the sum of the two single slit patterns. Left slit band plus right slit band. Just like the marbles, but that's not what you get. Instead, you get the interference pattern with its characteristic bright and dark stripes. The two-slit pattern is not the sum of the two one-slit patterns. There are places on the screen that receive many hits when only one slit is open, but receive almost no hits when both slits are open. Opening a second slit has somehow prevented electrons from landing where they used to land freely. This is impossible in any classical picture. In classical physics, opening an additional path can only increase the number of ways for a particle to reach a given point. it can never reduce the count to 0. If electrons were classical particles following definite paths, opening the second slit should add more electrons to every part of the screen, not remove them. The fact that the two-slit result isn't the sum of the single-slit results is direct experimental proof that something non-classical is happening. What's happening is interference between probability amplitudes. When both slits are open, the wave function of each electron passes through both slits simultaneously. On the other side of the barrier, the amplitude from the left slit and the amplitude from the right slit combine. At some locations on the screen, the two amplitudes add constructively, and the probability of the electron arriving there is high. At other locations, the two amplitudes cancel destructively, and the probability drops to nearly 0. The electron is never found in those dark regions, not because something is blocking it, but because the quantum amplitudes for arriving there via the left slit and via the right slit are equal and opposite, and they cancel perfectly. Now, this raises an obvious question. If the electron's wave function passes through both slits, does that mean the electron itself is in two places at once? Is it literally going through both slits simultaneously? This is where language becomes tricky and where many popular explanations go wrong. The honest answer is that physicists debate exactly what to say here, and the answer depends on how you interpret quantum mechanics. But there are things we can say precisely. And I want to be very careful about the distinction between what the experiment actually demonstrates and the stories we tell about it. What the experiment demonstrates, without any ambiguity, is this. The probability amplitudes associated with the electron's quantum state pass through both slits. The interference pattern proves this. You cannot explain the pattern without both paths contributing amplitudes that interfere on the far side. This is an experimental fact, not an interpretation. What the experiment does not demonstrate is that a tiny ball literally splits into two tiny balls, one going through each slit. The electron is not being duplicated. There aren't two electrons. There's one electron described by one wave function, and that wave function extends through both openings. The word physicists use for this is superposition. The electron is in a superposition of going through the left slit and going through the right slit. But superposition doesn't mean the electron is literally in two ordinary places at the same time the way you might be in two different chairs. It means the quantum state contains amplitudes for both possibilities, and those amplitudes contribute simultaneously to determining the final outcome. Think of it this way. If you pluck a guitar string, the vibration can be described as a combination of many different frequencies, all present at once. The string isn't in two places. It's executing one motion that is a superposition of simpler motions. The quantum wave function is similar in spirit. It's one mathematical object that encodes amplitudes for many possible outcomes simultaneously. Those amplitudes evolve, interact, and interfere. They are all present in the quantum state at the same time. But this doesn't mean there are multiple copies of the electron living in parallel. Now, here's where things become even more revealing. What happens if you try to find out which slit the electron actually went through? You might think this is a reasonable thing to do. After all, if the electron passes through the slits one at a time and lands as a single dot, surely it went through one slit or the other. Surely you could set up a tiny detector near the slits. Something that checks whether the electron passed through the left opening or the right opening without disturbing it too much. You can, in fact, set up such a detector. Physicists have done this many times using many different techniques. You can place a detector that records which slit the electron goes through, and the detector works. Every single time, it tells you the electron went through one slit, left or right. Never both, never neither. Always one definite answer. In this sense, the electron seems to behave like a classical particle. It goes through one opening. End of story. But when you perform this witch path measurement and then look at the detection screen, the interference pattern is gone. Completely gone. The beautiful alternating bright and dark stripes vanish. What you see instead is exactly the classical pattern. Two overlapping bands, the sum of the left slit pattern and the right slit pattern. No interference, no dark stripes, no cancellation. The act of determining which slit the electron passed through has destroyed the interference. And this happens every single time, regardless of how the witch path measurement is made. It doesn't matter how gentle or indirect your detection method is. If you gain enough information to determine which slit the electron used, the interference pattern disappears. If you don't gain that information, the interference pattern appears. This is not a matter of clumsiness or technological limitation. It's a fundamental feature of quantum mechanics. Information about the electron's path and the interference pattern are mutually exclusive. This is experimentally established beyond any reasonable doubt. Decades of increasingly refined experiments have confirmed it. You can even set up experiments where the witch path information is recorded, but then erased before anyone looks at it. These are called quantum eraser experiments, and they show something even more striking. If the witch path information is fully erased in the right way, the interference pattern comes back. The pattern's presence depends entirely on whether the witch path information exists in any physical record anywhere, not on whether a human being has looked at that record. The quantum eraser experiment deserves a closer look, because what it demonstrates is so counterintuitive that it borders on surreal. Here's how it works in its simplest form. You set up the double-slit experiment as before. Two slits, a detector screen behind them, electrons fired one at a time. But now you add a witch path detector, some device that records whether each electron went through the left slit or the right slit. As we discussed, when this witch path information is recorded, the interference pattern vanishes. You get the classical pattern instead. Two overlapping bands, no dark stripes, no cancellation. But now comes the twist. After the witch path information has been recorded, you erase it. You destroy the record. You eliminate any trace that could tell you which slit each electron went through. And when you do this in the right way, when the erasure is complete and no copy of the information survives anywhere in any physical system, the interference pattern comes back. Think about how strange this is. The electrons have already landed on the screen. Their dots are already recorded. The witch path detector had already registered which slit each electron passed through. The information existed. It was physically real, stored in a detector, encoded in atoms and electrical signals. And yet, erasing the information after the fact allows the interference to reappear. It's as if the electrons retroactively decided to behave like waves once the witch path information was destroyed. Now, I need to be careful here, because the quantum eraser doesn't actually involve backwards causation. The full explanation involves correlations between the electron and the witch path detector, and you only see the recovered interference pattern when you sort the detection events based on the eraser's results. The total unsorted pattern on the screen always looks like the classical pattern. The interference is hidden within subsets of the data, and you need the eraser's information to know which subset to look at. So nothing travels backward in time, no signal is sent into the past. But the result is still remarkable. Whether interference is visible in the data depends on which path information is available, even if that information is recorded and destroyed after the electron has already been detected. This experiment has been performed with both photons and atoms, and the results are always the same. Interference and which path information are complementary. You can have one or the other, but never both at the same time. And the decision about which one you observe can be delayed, made after the particle has already passed through the slits and struck the detector. This leads to an even more provocative version called the delayed choice experiment, first proposed as a thought experiment by the physicist John Archibald Wheeler. In Wheeler's version, the experimenter decides whether to measure which path the particle took, or whether to look for interference only after the particle has already passed through the double slit. The particle is already on the other side of the barrier, heading toward the detector, when the experimenter flips a switch that determines whether the apparatus will record which path information, or allow interference to occur. The result is exactly what quantum mechanics predicts. If the switch is set to record which path information, the interference pattern disappears, even though the electron passed through the slits before the switch was flipped. If the switch is set to allow interference, the interference pattern appears. The electron seems to have adjusted its behavior based on a choice that was made after it had already completed the relevant part of its journey. Again, this doesn't mean information travels backward in time. The correct explanation is that you cannot assign the electron a definite history, a definite story about what path it took, until the entire experimental arrangement is complete. The electron's behavior cannot be separated from the full context of the measurement. What happened at the slits depends, in a deep and irreducible way, on what happens later at the detector. This is not speculation. Delayed choice experiments have been performed in the laboratory, most famously by a team in 2007, using single photons in an interferometer. The results match quantum predictions exactly. The universe does not seem to assign the electron a definite path through the slits, independently of how the experiment is completed. The history of the particle and the measurement arrangement form an inseparable whole. And this reinforces the central point of the double-slit experiment even more powerfully than the basic version does. The electron before measurement cannot be described as following one definite classical path. Not only does the interference pattern prove this when no which path measurement is made, but the quantum eraser and delayed choice experiments show that even the question of whether the electron behaved as a wave or a particle depends on choices that can be deferred until after the electron has passed through the apparatus. Let me spell out what this means. When you don't measure which slit the electron goes through, the wave function passes through both slits. The amplitudes from the two paths interfere. You get the interference pattern. The electron cannot be described as having taken one definite path. If it had secretly gone through just one slit, there would be no interference. The interference proves that both paths contributed. When you do measure which slit the electron goes through, you gain definite information about the path. The electron went through the left slit, or it went through the right slit. One or the other. But now the interference is gone. The amplitudes from the two paths no longer cancel. The pattern on the screen is classical. The electron seems to be telling you something profound. If you don't ask which path it took, it doesn't take a definite path. Its quantum state evolves through both possibilities, the amplitudes interfere, and the result is a pattern impossible for any classical particle. But the moment you do ask, the moment you create a physical record of which path it chose, the electron commits to one path, and the interference vanishes. This isn't the electron being shy or coy. It's a direct consequence of how quantum states work. When the which path information becomes physically recorded in the environment, when a detector clicks or a photon scatters or any physical system becomes correlated with the electron's path, the quantum state of the electron becomes entangled with the state of the detector. The amplitudes for the two paths are no longer free to interfere because they've become linked to distinguishable states of the measuring device. The superposition hasn't disappeared from the mathematics, but the interference between the two paths has been suppressed because the two components of the superposition now label different states of the wider system. This process has a name that we'll explore in much more detail soon. It's called decoherence, and it plays a central role in explaining how definite measurement outcomes emerge from the quantum world. But let me not rush ahead. For now, I want you to sit with what the double-slit experiment has shown us, because the implications are enormous. First, the interference pattern proves that the electron's quantum state extends through both slits when no which path measurement is made. This is not a philosophical claim. It's an experimental fact derived directly from the pattern on the screen. No model in which the electron always travels through one definite slit can reproduce the observed interference. Second, when the electron arrives at the detector screen, it always arrives at one specific point. It's detected as a localized particle, single dot, single position. There's nothing blurry or spread out about the detection event itself. Third, the probability of the electron arriving at each location is determined by squaring the combined probability amplitudes from both paths. Where the amplitudes reinforce, many electrons land. Where they cancel, none land. The Born rule works perfectly. Fourth, if you determine which slit the electron passes through, the interference vanishes. The pattern becomes classical. The electron appears to have taken one definite path, but the interference is gone because the which path information has been recorded, destroying the conditions necessary for the amplitudes to interfere. These four facts together paint a picture that is impossible to reconcile with classical physics. In the classical world, an object always takes one definite path. It goes through one slit or the other, regardless of whether you're watching. The interference pattern says this is not what electrons do. Electrons don't secretly follow one classical path when you're not looking. If they did, the math doesn't work. The dark bands wouldn't exist. The two-slit pattern would simply be the sum of the single-slit patterns. And it is not. That sum has been measured, and it doesn't match. The interference pattern has been measured, and it does match the quantum prediction. The experiment has spoken. This is what physicists mean when they say quantum mechanics is not merely classical physics with a layer of randomness on top. It's not that the electron goes through one slit, and we just can't predict which one. The way we can't predict which face a flipped coin will show. If that were the case, the two-slit pattern would look classical. There would be no dark stripes. The fact that interference occurs means the quantum description is fundamentally different from any classical random process. The double-slit experiment doesn't just suggest that something non-classical is happening, it proves it. The interference pattern is the smoking gun. It's a physical record, imprinted on the detector screen, of the fact that the electron's quantum state encompassed both paths simultaneously, not as a metaphor, not as a mathematical trick, but as a real feature of the physical world that leaves visible, measurable traces. So now we have a picture, incomplete but powerful, of what an electron is doing before you measure its position. Its wave function evolves through space, assigning probability amplitudes to many possible locations. Those amplitudes can pass through multiple openings simultaneously. They can interfere, reinforcing in some places, cancelling in others. When the electron finally encounters a detector, it appears at one specific point, selected randomly according to the probabilities given by the Born rule. But what exactly happens at that moment of detection? What turns a spread out wave function into a single definite dot on a screen? And why don't we see interference in the everyday world around us? Why don't baseballs and cats and people exhibit this kind of behavior? These questions take us from the experiment itself to the process of measurement. And the answers, it turns out, involve not consciousness, not magic, not philosophy, but physics. The physics of what happens when a tiny quantum system interacts with something enormously large. We've arrived at one of the deepest problems in all of physics. The double-slit experiment showed us that before measurement, an electron's quantum state can extend through both slits simultaneously. The probability amplitudes for different paths interfere. An interference pattern appears on the screen. The electron doesn't seem to follow one definite classical trajectory. But when the electron hits the detector screen, all of that richness collapses into a single event. One dot, one location, one definite outcome. Every single time you detect an electron, you find it at one specific spot, never smeared across many spots, never split between two locations, one point, one result. So something happens between the quantum state with all its extended amplitudes and the definite result recorded in the detector. Something turns possibility into actuality. Something converts a wave function that spans many positions into a single measured outcome. What is that something? What physically occurs during a measurement? This question has troubled physicists for nearly a century, and different interpretations of quantum mechanics offer different answers, which we'll explore later. But there are things we can say about the process of measurement that are grounded in physics rather than philosophy. Things we can test in the laboratory. And the most important of these involves understanding what a measurement device actually is and what happens when a quantum system interacts with one. Let's think carefully about what a detector does. Take the simplest example. Suppose you're trying to detect the position of an electron, and your detector is a screen coated with a material that produces a tiny flash of light whenever an electron strikes it. A fluorescent screen. Something similar to the screens used in old cathode ray tube televisions. When an electron hits the screen, it interacts with the atoms in the coating. It transfers energy to those atoms. Those atoms become excited and emit photons. The photons travel to your eye or to a camera, and the flash is recorded. A dot appears. Notice what happened. The electron didn't just pass by the screen quietly, it interacted with it. It exchanged energy with the atoms in the screen. Those atoms changed their state. The photons they emitted carried information about where the interaction occurred. That information propagated outward, reaching other systems, a camera, a computer, a photograph, a human eye. The location of the interaction became a physical record, imprinted in the state of billions of atoms in the screen, in the pattern of photons that flew outward, in the electrical signals running through the camera's circuits. The information about where the electron landed didn't stay confined to the electron. It spread into the environment. This spreading is the key to understanding measurement. Before the electron hits the screen, its wavefunction assigns amplitudes across many locations. The screen, with its trillions of atoms, is sitting there in a definite macroscopic state, ready and waiting. When the electron arrives and interacts with the screen at one particular location, the state of the electron becomes correlated with the state of the screen at that location. The atoms near the impact site get excited. Atoms far from the impact site don't. The screen's state now records where the electron arrived. This correlation between the quantum system and the much larger measuring device is the physical essence of measurement. But there's a subtlety here that goes to the heart of the problem. Quantum mechanics says the electron's wavefunction assigns amplitudes to many positions. If the measurement interaction is itself governed by quantum mechanics, and it must be because quantum mechanics governs all physical interactions, then in principle, the full quantum state of the electron plus the screen should be a superposition. Not just the electron in a superposition of positions, but the electron plus the screen together in a superposition of correlated states. Amplitude for the electron being here and the screen showing a flash here, plus amplitude for the electron being there and the screen showing a flash there, plus amplitude for every other position. This is exactly the puzzle that the physicist Erwin Schrödinger dramatized in 1935 with his famous thought experiment involving a cat. It's a thought experiment so famous that even people who know nothing else about quantum mechanics have heard of it. And despite being nearly 90 years old, it cuts directly to the heart of the measurement problem. Imagine a sealed box. Inside the box is a cat, a small amount of radioactive material, a radiation detector like a Geiger counter, and a vial of poison. The setup works like this. Over the course of 1 hour, there is a 50% chance that one atom of the radioactive material will decay. If it does, the Geiger counter detects the radiation. The counter triggers a mechanism that breaks the vial of poison. The poison is released, and the cat dies. If no atom decays, nothing happens, and the cat remains alive. Now, here's the problem. The radioactive atom is a quantum system. Before any measurement detects whether it has decayed, quantum mechanics describes it as being in a superposition of decayed and not decayed. But the atom is connected to the Geiger counter, which is connected to the poison mechanism, which is connected to the cat. If quantum mechanics applies to all of these systems, and it must because they're all made of atoms and electrons governed by quantum laws, then the superposition should propagate all the way up the chain. The quantum state of the entire contents of the box should be a superposition. Amplitude for the atom having decayed, the counter having clicked, the vial having broken, and the cat being dead. Plus amplitude for the atom not having decayed, the counter being silent, the vial being intact, and the cat being alive. The cat, according to the pure mathematics, is in a superposition of alive and dead. Now, Schrödinger did not propose this experiment because he believed cats could actually be in superpositions of alive and dead. He proposed it to show that something is deeply strange about how quantum mechanics connects to the macroscopic world. If superposition works perfectly well for electrons and atoms, at what point does it stop working? At what point does the quantum description with its multiple simultaneous possibilities give way to the definite classical reality we experience every day? The cat is clearly either alive or dead when you open the box. You never see a blurry mixture of a live and dead cat. So something must happen to resolve the superposition. But what? This is the measurement problem, stated as sharply as possible. The pure Schrödinger equation, the equation that governs how quantum states evolve, never produces a single definite outcome. It just keeps generating larger and larger superpositions as the quantum system interacts with its surroundings. Yet, we always observe definite outcomes. One result, not a blur of many results. One cat alive or dead. One electron detected here or there. The mathematics seems to predict ambiguity, but the world delivers certainty. Something bridges that gap, and understanding what that something is remains one of the central unsolved problems in the foundations of physics. If you wrote down the quantum state of the total system rigorously, you wouldn't get one definite outcome. You get a superposition of many outcomes, each correlated with a different state of the screen. From the pure mathematics alone, nothing seems to select one outcome over the others. The equation that governs how quantum states evolve, known as the Schrödinger equation, is perfectly smooth and deterministic. It never says the wavefunction suddenly jumps to one answer. It just keeps evolving, spreading the superposition to larger and larger systems. So, where does the definite outcome come from? This is where decoherence enters the picture. Decoherence is a physical process, not a philosophical idea, and understanding it is essential to understanding how the quantum world connects to the world you experience every day. Here's the core insight. A measuring device like a detector screen is not a small, isolated quantum system. It's enormous by quantum standards. A typical detector contains something on the order of 10 to the 23rd atoms. That's roughly the number given by Avogadro's number, the count of atoms in a modest lump of matter. These atoms are constantly vibrating, jostling, interacting with each other and with the surrounding environment. Photons bounce off the screen, air molecules collide with its surface, thermal vibrations ripple through its structure. The screen is coupled to an overwhelmingly complex environment composed of countless particles. When the electron's quantum state becomes correlated with the screen's state in turn becomes correlated with the environment. The flash of light emitted by the excited atoms travels outward and interacts with air molecules, walls, cameras, and everything else nearby. The thermal vibrations of the atoms at the impact site spread through the screen and into the table supporting it. Information about the measurement outcome leaks into the environment almost instantly, carried by an enormous number of particles moving in an enormous number of directions. Here's why this matters. Remember that inner interference, the hallmark of quantum behavior, requires the probability amplitudes for different outcomes to combine coherently. The peaks and troughs of the two amplitudes have to align properly for constructive or destructive interference to occur. If the amplitudes get out of step, if their phases become scrambled and random relative to each other, the interference washes out. It doesn't cancel cleanly. It just averages away into noise. When the measurement outcome gets recorded in the states of trillions of environmental particles, each component of the superposition becomes linked to a different configuration of that enormous environment. The amplitude for the electron landing at location A is now correlated with one particular arrangement of trillions of environmental particles. The amplitude for it landing at location B is correlated with a completely different arrangement. For these two components to interfere, you'd need those trillions of particles to line up precisely. Their phases perfectly synchronized. The probability of that happening is not just small, it is so close to zero that it would never occur in the lifetime of the observable universe. This is decoherence. The quantum interference between different measurement outcomes doesn't disappear from the mathematics. In principle, the total quantum state of the electron plus the screen plus the environment still contains all the superposed terms, but the ability of these terms to produce observable interference effects gets destroyed, completely and irreversibly, for all practical purposes, by the entanglement with the environment. The different outcomes become, as physicists say, decoherent. They can no longer interfere with each other in any way that could ever be detected. After decoherence, what remains looks exactly like a classical probability distribution. There's some probability the electron landed here, some probability it landed there. But now these are ordinary classical probabilities, like the probability that a flipped coin is heads or tails. The quantum weirdness, the ability of the amplitudes to interfere, has been washed out by the environment. The system behaves as though one definite outcome occurred, even though the underlying mathematics still contains all the terms. This is why we don't see quantum interference in everyday life. You don't observe your cat in a superposition of being on the couch and being on the windowsill. You don't see baseballs interfering with themselves. Every macroscopic object is constantly interacting with an overwhelming number of environmental particles, photons, air molecules, thermal vibrations, even cosmic background radiation. Any quantum superposition involving a macroscopic object decoheres almost instantly. The time it takes is astonishingly short. For a dust grain floating in air, decoherence occurs in roughly 10 to the minus 31 seconds. That's a decimal point followed by 30 zeros and then a 1. Far faster than any process you could ever hope to observe. By the time you could even begin to look, the interference has already been wiped out. For an object the size of a baseball, decoherence happens so fast it might as well be instantaneous. The baseball is constantly bombarded by photons, air molecules, and thermal radiation. Its quantum state is entangled with the environment in ways far too complex for any interference to survive. This is why the classical world looks classical. Not because quantum mechanics stops applying at large scales. Quantum mechanics applies everywhere and always, but because decoherence destroys observable interference so rapidly and so thoroughly that macroscopic objects always appear to have definite positions, definite velocities, definite properties. The quantum behavior is still there in principle, hidden in the correlations between the object and its environment, but it can never be detected. The concept of decoherence was developed primarily through the work of H.D. Taze in the 1970s and Wojciech Zurek in the 1980s and 90s. It has since become one of the most important ideas in modern physics. Decoherence explains why quantum effects are hard to observe at large scales. It explains why measuring devices produce definite outcomes. It explains why your coffee cup sits on the table without being in a quantum superposition of all possible positions. It bridges the gap between the quantum world and the classical world not by saying quantum mechanics breaks down, but by showing that its effects become unobservable when large numbers of particles are involved. Let me walk through a specific example to make decoherence concrete, because the abstract description only takes you so far. Imagine a single electron heading toward a detector screen. Its wavefunction assigns amplitudes to two locations, position A on the left side of the screen and position B on the right side. Before the electron arrives, both amplitudes are present and they can interfere. Now the electron hits the screen at position A. What happens physically? The electron collides with an atom in the screen's fluorescent coating at that location. The collision transfers energy to the atom, kicking one of its own electrons into a higher energy state. That excited atom quickly drops back down and emits a photon, a tiny flash of light, traveling outward from position A. That photon strikes a neighboring atom, which absorbs it and re-emits another photon in a slightly different direction. Meanwhile, the kinetic energy from the original impact sends a vibration rippling through the lattice of atoms in the screen. That vibration spreads outward, jostling neighboring atoms, which jostle their neighbors, converting the energy into heat distributed across billions of atoms. Within a billionth of a second, information about the electron's landing site has been copied into the states of millions of particles. Photons are flying outward. Atoms are vibrating differently near position A than they are near position B. The pattern of thermal energy in the screen is different from what it would have been if the electron had landed at position B instead. A camera sensor absorbs some of the emitted photons, triggering electrical signals in its circuits. Those signals propagate through wires, changing the states of yet more atoms and electrons. Every one of these physical processes entangles the measurement outcome with the environment. The amplitude for the electron at position A is now linked to one specific configuration of this enormous cascade of particles. The amplitude for position B would have been linked to a completely different cascade. For these two components to interfere, every single one of those millions of particles would need to be in precisely the right state. The probability of that happening by chance is so unimaginably small that it makes winning every lottery on Earth simultaneously look like a certainty by comparison. The interference is gone, permanently and irrecoverably. Now, I want to address something that popular culture has gotten terribly wrong about quantum measurement. You've probably heard the claim that conscious observation is required to make a quantum measurement, that the electron's wave function doesn't settle into a definite outcome until a conscious mind looks at it. That human awareness plays some special role in quantum physics. This is wrong. There is no evidence whatsoever that consciousness has anything to do with quantum measurement. None. A Geiger counter can detect a radioactive decay without anyone watching it. The detector clicks. The click is recorded in the physical state of the detector's electronics. The information is there, stored in atoms and electrical signals, whether or not any human ever looks at the readout. The decoherence that destroys quantum interference happens because of the physical interaction between the quantum system and the atoms in the detector, not because a human brain gets involved. A camera can record a measurement. A computer can record a measurement. A rock being struck by a particle and heating up slightly is, in a sense, recording a measurement. Consciousness is nowhere in the physics. The confusion arose partly from early and somewhat careless language used by some of the founders of quantum mechanics. The word observer appears frequently in old textbook discussions. and people understandably interpreted observer as meaning a conscious being. But in the technical physics, observer simply means any physical system that records information about the quantum system. A photographic plate is an observer. A magnetic tape is an observer. An atom that absorbs a photon and changes its energy state is an observer. The universe was performing quantum measurements for billions of years before conscious beings existed. Stars were emitting photons. Those photons were being absorbed by atoms in interstellar gas. Each absorption event was a measurement that produced a definite outcome. No consciousness required. The universe didn't need us to work. So, to summarize what we've learned about measurement, when an electron interacts with a measuring device, the electron's quantum state becomes correlated with the state of the device. The device's state in turn becomes correlated with the surrounding environment. This process of decoherence destroys the ability of different measurement outcomes to interfere with each other. What's left is, for all practical purposes, a situation where one definite outcome has occurred. The probability of each outcome is given by the Born rule, by squaring the wavefunction's amplitude at each position. This is all physics. No consciousness, no magic, no philosophy is required to explain why detectors produce definite results. But decoherence, powerful as it is, does not by itself answer every question about measurement. It explains why we don't see interference between macroscopic outcomes. It explains why measurement devices give definite results, but it doesn't, on its own, tell you why this particular outcome occurred rather than that one. It doesn't explain why the electron landed here rather than there. It removes the interference, but it leaves you with a set of possible outcomes and their probabilities, and it doesn't select one. This remaining question, why one outcome rather than another, is where different interpretations of quantum mechanics disagree, and we'll come to that before the night is over. I want to pause here and state this gap clearly because it's genuinely important and it's often glossed over in popular explanations. Decoherence is sometimes described as though it solves the measurement problem. It doesn't. What decoherence does is explain why we don't see interference between macroscopic outcomes. It explains why the cat appears to be either alive or dead and never a blurry combination. It explains why your measuring instruments always show one definite reading. It removes the weirdness of macroscopic superposition by showing that the interference terms become unobservable when the environment gets involved. But decoherence doesn't explain why you see this outcome, and not that one. After decoherence, the mathematics of quantum mechanics still contains all the terms in the superposition. The amplitude for the electron at position A and the amplitude for the electron at position B are both still present in the total quantum state of the universe. Decoherence has made them unable to interfere with each other. They've become separate branches, decoupled, unable to exchange information. But nothing in the mathematics of decoherence selects one branch and discards the others. Nothing in the Schrödinger equation says this particular outcome happens and that one doesn't. So the question remains, if the equation doesn't pick one outcome, what does? Is there an additional physical process, a genuine collapse that selects one result and eliminates the rest? Or do all outcomes occur in separate branches of reality, as the many worlds interpretation claims? Or does the electron have a hidden definite position all along, guided by a pilot wave, so that the question of which outcome occurs was already settled before decoherence even happened? These are the questions that decoherence leaves unanswered, and they are not small questions. They are questions about the fundamental nature of reality. about whether the universe is deterministic or genuinely random, about whether other branches of the wave function are real or merely mathematical artifacts, about what it means for something to happen at the deepest level of physical law. Decoherence is a crucial piece of the puzzle. It explains how the classical world emerges from quantum mechanics in every experiment we can actually perform. But it is not the whole puzzle. The rest belongs to interpretation, and that is where we'll turn at the end of our journey tonight. For now, let's turn to the last major concept we need to explore. A concept that is arguably the most misunderstood idea in all of physics. The Heisenberg uncertainty principle. Werner Heisenberg formulated this principle in 1927, and it is one of the foundational pillars of quantum mechanics. But almost everything you've heard about it in popular culture is probably wrong. So let me explain what it actually says and why it matters. You've likely heard the uncertainty principle described something like this. You can't measure where something is and how fast it's moving at the same time, because the act of measuring one property disturbs the other. As if the problem is that your measuring instrument is too clumsy. As if you bump the electron when you try to see it, and that bump changes its velocity. This description makes it sound like the uncertainty principle is about measurement limitations. About the fact that our instruments aren't good enough. As if, with the sufficiently gentle measurement device, you could in principle know both the position and momentum of an electron simultaneously and with perfect precision. This is not what the uncertainty principle says. The principle is not about measurement disturbance. It's about the nature of quantum states themselves. Here's what it actually tells you. In quantum mechanics, certain pairs of physical properties are linked in a fundamental way. Position and momentum are the most famous pair. The uncertainty principle says that no quantum state exists in which an electron has both a perfectly precise position and a perfectly precise momentum at the same time. This is not a limitation of your instruments. This is a property of every possible quantum state that the universe allows. Even with perfect instruments, even with technology far beyond anything we can currently build, even in principle, you cannot prepare an electron in a state that simultaneously has an exact position and an exact momentum. Such a state does not exist in the mathematics of quantum mechanics. It's not forbidden by some arbitrary rule. It simply isn't there amongst the possible states that quantum theory permits. Let me explain why. Think back to the wave function. An electron's position wave function assigns amplitudes to various locations in space. If that wave function is tightly concentrated at one point, a narrow spike, then the electron has a very well-defined position. If you measure it, you'll find it very close to that spike. The position is nearly certain. But here's the connection. A wave function that is tightly concentrated in space must, by the mathematics of wave behavior, be composed of a very wide range of momentum components. This isn't a quantum rule that was imposed by a committee. It's a mathematical property of waves themselves. You can demonstrate it with sound waves, water waves, any type of wave at all. If you want a wave that is very localized, squeezed into a tiny region, you need to add together many different wavelengths. This is consequence of Fourier analysis, a branch of mathematics that describes how any shape can be built from combinations of simple waves. The more localized you make the shape, the more wavelengths you need to include. In quantum mechanics, an electron's wavelength is directly related to its momentum. This relationship was proposed by Louis du Broglie in 1924 and has been confirmed by every experiment since. Short wavelength means high momentum, long wavelength means low momentum. So a wave function that is tightly localized in position, which requires many different wavelengths, necessarily involves a wide spread of momenta. The position is well defined, but the momentum is uncertain. The electron's quantum state simply doesn't have a definite momentum in this situation. The reverse is equally true. If you prepare an electron with a very well-defined momentum, its wave function must be a long, extended wave with a single wavelength stretching across a large region of space. This means the electron's position is very poorly defined. It could be found almost anywhere along that extended wave. The momentum is sharp, but the position is uncertain. This trade-off is unavoidable. It's built into the mathematical structure of waves. Any quantum state you pick will have some spread in position and some spread in momentum. You can make one smaller, but only at the cost of making the other larger. The product of the two spreads can never be smaller than a fixed minimum value, related to Planck's constant, the fundamental quantum of action. This minimum is the uncertainty principle. Let me say it once more, because this is crucial. The uncertainty principle is not telling you that your measurement of position kicks the electron and randomizes its momentum. It's telling you that before you measure anything, the quantum state itself doesn't have both a sharp position and a sharp momentum. There is no hidden precise value being disturbed. The spread is in the quantum state, not in the measurement process. This can be tested directly. You can prepare millions of electrons in identical quantum states. For some of them, you measure position. For others from the same batch, you measure momentum. Each individual measurement gives a definite result, but the results vary from trial to trial. The spread in the position results and the spread in the momentum results always satisfy Heisenberg's inequality. The tighter the position spread, the broader the momentum spread. Always. Without exception. No cleverness in your experimental design can beat this. You're not being outsmarted by nature. Nature isn't hiding precise values behind a shield. The quantum state genuinely doesn't encode both values precisely. Asking for the exact position and exact momentum of an electron is like asking for the exact location of a musical note. A pure musical tone, a single precise frequency, extends over a long duration. It's everywhere in time. If you want a very short sound, a click, it contains many different frequencies. You can have a precise frequency or a precise time, but not both. It's not that your ears aren't good enough. It's that the sound itself doesn't have both properties simultaneously. The uncertainty principle applies to every quantum system, every particle, every atom, every molecule, and it applies to other pairs of properties besides position and momentum. Energy and time are related by a similar trade-off. If a quantum state exists for a very short time, its energy is uncertain. If you want a very precise energy, the system must persist for a long time. Spin components along different axes also obey uncertainty relations. The principle is woven into the fabric of quantum theory at the deepest level. This has consequences that ripple through all of physics. The uncertainty principle is why atoms are stable. In classical physics, an electron orbiting a nucleus should radiate energy and spiral inward, crashing into the nucleus in a tiny fraction of a second. Every atom should collapse almost instantly, but the uncertainty principle prevents this. If the electron were confined too tightly near the nucleus, its position would be very well defined, and its momentum would become very uncertain, meaning it would have a lot of kinetic energy. This energy pushes back against the confinement. The atom reaches a balance between the electrical attraction pulling the electron inward and the uncertainty-driven kinetic energy pushing it outward. This balance is what determines the size of atoms. The uncertainty principle is literally the reason matter is stable and has the structure it does. Now, stepping back, think about what we've covered in this part of our journey. We've seen that measurement is a physical process in which a quantum system becomes correlated with a large measuring device, and decoherence rapidly destroys quantum interference between different outcomes. This happens because the measurement outcome gets imprinted in the states of an overwhelmingly large number of environmental particles, making interference practically impossible. Consciousness plays no role. Any physical interaction that records information counts. And we've seen that the uncertainty principle is not a statement about clumsy instruments. It's a fundamental feature of quantum states. Certain pairs of properties simply cannot both be sharply defined at the same time. This is not a limitation of technology. It is a limitation of reality, or at least of reality as quantum mechanics describes it. Both of these insights, decoherence and the uncertainty principle, reinforce the same central message. The electron before measurement is not a tiny classical ball with a hidden definite position and a hidden definite momentum that we simply can't access. The quantum state is the description. The amplitudes are the description. The spread, the superposition, the interference, these aren't artifacts of ignorance. They appear to be features of the physical world itself. But does this mean the electron truly has no definite position before measurement? Or could there be some deeper level of reality underneath the wave function? Some hidden structure that does assign definite positions, but that quantum mechanics simply doesn't capture? Could the wave function be incomplete? The way a weather forecast is incomplete because it doesn't track every air molecule? These questions take us beyond what experiments alone can answer and into the realm of interpretation. Because different interpretations of quantum mechanics give fundamentally different answers to the question of what exists between measurements. And the remarkable thing is that the disagreement isn't about the numbers. The mathematics works. The predictions are confirmed. What remains fiercely contested is what the mathematics is telling us about the world between one measurement and the next. We've come a long way together tonight. We start with the familiar classical world where objects sit in definite places whether anyone looks or not. We watch that picture break apart when we zoom down to the scale of electrons. We saw the wave function and its probability amplitudes. We watched the double-slit experiment prove that an electron's quantum state can extend through two paths simultaneously, producing interference that no classical particle could ever create. We explored what happens during measurement, how decoherence destroys quantum interference when a tiny system interacts with something enormously large, and how the uncertainty principle is not about clumsy instruments, but about the fundamental nature of quantum states themselves. Now we arrive at the deepest question. We know what quantum mechanics predicts. We know those predictions are confirmed by experiment to extraordinary precision. But what does the theory mean? What is actually happening to the electron between measurements? Is the wave function a complete description of reality, or is it missing something? Does the electron truly lack a position before measurement, or does it have one that the theory simply doesn't capture? Here is where we enter the territory of interpretation. And I need to tell you something important up front. The differences between them are not about what you'll see in the laboratory. Every interpretation we're about to discuss predict the same outcomes for every experiment ever performed. The disagreements are entirely about what story you tell about what's happening when you're not looking. This is an extraordinary situation in the history of science. Multiple fundamentally different pictures of reality, all equally consistent with every observation ever made. Physicists don't agree on which picture is correct, and they may never agree unless someone devises an experiment that can tell the interpretations apart. But let me walk you through the major ones, because each illuminates the question of where the electron is before measurement from a different angle. And understanding the range of possibilities is itself deeply instructive. The oldest and most widely taught interpretation is the Copenhagen interpretation, associated primarily with Niels Bohr and Werner Heisenberg, who developed it in the late 1920s. The Copenhagen interpretation takes a deliberately cautious stance. It says the wave function is a tool for predicting measurement outcomes, and you should not ask what the electron is doing between measurements. Before you measure its position, the electron does not have a definite position. Not because it's hiding one from you, not because your instruments are too limited. The position simply doesn't exist as a definite property of the electron until a measurement brings it into being. The wave function is the most complete description that nature allows. There is nothing underneath it, no hidden reality waiting to be uncovered. In Copenhagen, the act of measurement is special. When a measurement occurs, the wave function changes abruptly. It goes from a spread out state with amplitudes across many positions to a state concentrated at the location where the electron was actually found. This sudden change is sometimes called the collapse of the wave function. Before measurement, many outcomes are possible. After measurement, one outcome has occurred. The collapse is how Copenhagen accounts for the transition from quantum possibilities to a definite classical result. Copenhagen has been enormously successful as a practical framework. Most working physicists use it daily. You apply the Born rule, calculate probabilities, compare with experiments, and the theory works spectacularly well. But Copenhagen has always made some physicists uncomfortable. Why is measurement special? What exactly counts as a measurement? If the entire universe is governed by quantum mechanics, why does the wave function obey one rule? The smooth Schrödinger equation most of the time, but then suddenly obey a different rule, collapse during measurement. Copenhagen doesn't fully answer these questions. It draws a line between the quantum system and the classical measuring apparatus and says, don't ask what happens at the boundary. For many physicists, this feels less like an answer and more like a refusal to answer. A radically different approach was proposed in 1957 by Hugh Everett, a young physicist who took quantum mechanics at face value and asked what happens if you never invoke collapse at all. What if the Schrödinger equation is always valid, with no exceptions, no special measurement rule, no collapse? This leads to the many worlds interpretation. In many worlds, when a measurement is performed, the wave function doesn't collapse. Instead, all possible outcomes occur. The universe splits, or more precisely, the quantum state branches into components that no longer interfere with each other. In one branch, the electron is detected at position A and the experimenter sees it there. In another branch, the electron is detected at position B and the experimenter sees it there. Both branches are equally real, both experimenters exist, but the branches have decohered, meaning they can't interact with or detect each other. Each experimenter sees one definite result and has no access to the other branches. In many worlds, the electron before measurement genuinely doesn't have one definite position. Its wave function extends across many positions, and all of those possibilities are realized in different branches of the universal quantum state. There's no collapse. There's no special role for measurement. The Schrödinger equation just keeps running, and the apparent definiteness of measurement outcomes arises because each branch of the wave function contains an observer who sees one result. This interpretation has elegant features. It takes the mathematics of quantum mechanics completely seriously without adding any extra rules. But it comes at a staggering conceptual price. Every quantum event causes the universe to branch. The number of branches grows without limit. There are more branches than atoms in the observable universe, more than any number you could ever write down. Most physicists find this either exhilarating or absurd, and reasonable people disagree about which reaction is more appropriate. Critics also ask how probability fits in. If all outcomes occur, what does it mean to say one outcome has a 70% probability and another has 30%? Everett and his followers have proposed answers to this, but not everyone finds them convincing. Now, there's a third major approach that takes a completely different path from both Copenhagen and many worlds. This is the pilot wave theory, also called Bohmian mechanics, developed by David Bohm in 1952, building on earlier ideas from Louis du Broglie. In pilot wave theory, the electron does have a definite position at all times, even before measurement. Even between measurements. The electron is always a particle with a precise location, tracing a definite path through space. This sounds like classical physics, and in some sense it is. The electron is a real particle at a real place, but there's a crucial addition. Alongside the particle, there exists a wave function, the pilot wave, that guides the particle's motion. The pilot wave evolves according to the Schrödinger equation, exactly as in standard quantum mechanics. It extends through space, passes through both slits in the double-slit experiment, and develops all the interference structure we discussed. The particle itself goes through only one slit, but its trajectory is guided by the pilot wave, which went through both. The pilot wave pushes the particle toward regions where the amplitude is large and away from regions where the amplitude is small. This guidance reproduces all the statistical predictions of standard quantum mechanics. The interference pattern builds up. The Born rule probabilities emerge. Everything matches. So in pilot wave theory, the electron always has a position. The wave function is not the complete description. There's something extra, the particle's actual location, that quantum mechanics in its standard form doesn't include. The wave function is real and important because it guides the particle, but the particle has definite properties that the wave function alone doesn't specify. Pilot wave theory reproduces every prediction of standard quantum mechanics. Every experiment that confirms quantum theory also confirms pilot wave theory, because the two make identical predictions for all measurable quantities. The differences are entirely about what's happening behind the scenes. In Copenhagen, the electron has no position before measurement. In pilot wave theory, it has one. But the theory says you can never determine it more precisely than the wave function allows. The hidden position is real but inaccessible. The uncertainty principle still holds as a practical limitation on what you can know, even though the electron itself is always somewhere specific. This raises a fascinating philosophical question. If the hidden position can never be directly observed, if every measurement you perform gives results identical to standard quantum mechanics, does it matter whether the position is real? Is a hidden reality that can never be detected genuinely different from no reality at all? Different physicists answer this differently, and neither answer can be called wrong based on current evidence. There are other interpretations worth mentioning briefly. Objective collapse theories, sometimes called GRW theories after the physicists Girardi, Rimini, and Weber, modify the Schrödinger equation itself. They add a small random term that causes the wave function to spontaneously collapse from time to time, even without measurement. For a single electron, spontaneous collapses are incredibly rare, so the electron behaves quantum mechanically for all practical purposes. But for a macroscopic object made of trillions of particles, the collapses happen frequently enough that the object's wave function stays concentrated around a definite position. This explains why big things have definite locations without invoking a special measurement rule or branching universes. The appealing thing about objective collapse theories is that they make predictions slightly different from standard quantum mechanics. These spontaneous collapses introduce tiny deviations that could, in principle, be detected experimentally. Physicists are actively looking for these deviations. So far, none have been found, which constrains the theories but doesn't rule them out. There's also cubism, which takes an even more radical stance. It says the wave function doesn't describe the electron at all. It describes the beliefs of the person using the theory. Quantum mechanics, in this view, is a tool for an agent to organize their expectations about future experiences. The wave function is subjective, like a personal probability assignment, and the question of what the electron is doing between measurements is simply not one the theory is designed to answer. And there are relational interpretations associated with the physicist Carlo Rovelli, which argue that quantum states are not absolute properties of systems, but descriptions relative to a particular observer. The electron's wave function relative to one observer might be different from its wave function relative to another, and neither is more correct. Reality, in this view, is fundamentally relational. Properties don't exist in isolation. They exist in the relationship between systems. I've listed several interpretations, and you might wonder why physicists haven't simply done an experiment to settle the question. The reason is remarkable and deserves emphasis. Every interpretation that's taken seriously by working physicists reproduces the same experimental predictions. Copenhagen, many worlds, pilot wave theory, they all predict the same interference patterns, the same Born rule probabilities, the same uncertainty relations, the same measurement outcomes. The experimental data can't distinguish them. They agree on every number that a detector can record. They disagree only on what's happening when no detector is recording anything. This means the choice between interpretations is currently not an experimental question. It's a question about what we consider a satisfying explanation, about what picture of reality we find most coherent, most elegant, most economical. Different physicists weight these criteria differently, and so they arrive at different preferences. Some find Copenhagen's refusal to describe the unmeasured world appropriately humble. Others find it evasive. Some find many worlds mathematically pure and beautiful. Others find its proliferation of unobservable branches absurd. Some find pilot wave theory reassuringly concrete. Others find its hidden variables unsatisfying because they can never be directly observed. there is one important experimental result that constrains the interpretations. In 1964, the physicist John Stuart Bell proved a remarkable theorem. He showed that if an electron has definite properties before measurement, and if those properties are purely local, meaning they're not influenced by distant events happening faster than light, then the measurement results must obey certain mathematical inequalities, now called Bell inequalities. Let me give you an intuitive sense of what Bell was actually testing, because the logic is beautiful and the result is devastating for the classical picture of reality. Imagine you have two electrons that were prepared together in a special, correlated quantum state. You send one electron to a laboratory on the left side of a city and the other to a laboratory on the right side. The two laboratories are far apart. Nothing happening in one lab can possibly influence the other in time, because no signal, not even light, can cross the distance fast enough. In each laboratory, a physicist measures a property of their electron. They can choose to measure along different directions, and they make their choices randomly and independently. After thousands of trials, the two physicists compare their results. Now, here's Bell's key insight. If each electron carried a definite, predetermined value for every possible measurement direction, like a tiny instruction card telling it how to respond, no matter which direction the physicist chose, and if the two electrons couldn't communicate with each other during the experiment, then the correlations between the two sets of results would be limited. There's a mathematical ceiling on how strongly correlated the results can be. The two physicists' outcomes could agree often, but not too often. Their results could be correlated, but only up to a specific bound. This bound is the Bell inequality. Think of it like this. If two students take a multiple choice exam in separate rooms with no way to communicate, and they've studied from the same textbook, their answers will be correlated. They'll agree on many questions, but there's a limit to how often they can agree, determined by the information they each carried into the room. If they agree more often than that limit allows, something else is going on. Maybe they're secretly passing notes. Maybe there's a hidden communication channel you didn't account for. Bell showed that quantum mechanics predicts correlations that exceed this limit. The two electrons, measured in certain combinations of directions, should agree more often than any predetermined instruction cards could explain. More often than any local hidden reality permits. The quantum prediction exceeds the Bell inequality, and this is not a subtle violation, a borderline case that might be explained by experimental error. The quantum prediction exceeds the classical limit by a wide margin. The mathematics is precise. The difference between what local hidden variables allow and what quantum mechanics predicts is large enough to be measured clearly and unambiguously. The question then becomes simple. Does nature obey the Bell inequality as it must if electrons carry predetermined local properties? Or does nature violate it as quantum mechanics predicts? Experiments testing Bell inequalities have been performed many times, with increasing precision, and the results consistently violate the inequalities. Nature does not obey the constraints that local hidden variable theories require. This doesn't rule out all hidden variable theories. Pilot wave theory, for example, is a non-local hidden variable theory. The pilot wave connects distant particles, allowing correlations that violate Bell inequalities. So pilot wave theory is consistent with Bell's results. But any interpretation that wants to give the electron a definite pre-measurement position must accept non-locality. The idea that the quantum state connects distant parts of the universe in ways that classical physics doesn't allow. This is a real physical constraint, established by experiment, not by philosophy. So, where does all of this leave us? Let me bring the entire journey together and answer the question we started with. Where is an electron before you measure it? The honest answer, the answer that respects both the extraordinary experimental evidence and the genuine limits of what we currently know, goes like this. Quantum mechanics, the most rigorously confirmed theory that human beings have ever produced, describes the electron before measurement using a wavefunction. That wavefunction assigns probability amplitudes across many possible positions. It does not generally single out one position as the real one. The amplitudes evolve over time. They can extend through multiple regions of space simultaneously. They interfere with each other, producing effects like the double-slit interference pattern that are flatly impossible if the electron is secretly at one definite location. When a measurement is performed, when the electron interacts with a large measuring device, decoherence rapidly destroys the interference between different possible outcomes. One definite result is recorded. Where the electron will be found on any given trial is random, but the likelihood of each location follows precisely from the squared amplitude of the wavefunction. Repeated experiments match the predicted probability distribution with a consistency that no other theory in science can rival. Some interpretations of quantum mechanics, like Copenhagen, say the electron genuinely has no definite position before measurement. The wave function is the complete story. There is nothing more to say. Other interpretations, like pilot wave theory, say the electron does have a definite position at all times, but that position is guided by the wave function and can never be determined more precisely than the wave function allows. Still, other interpretations, like many worlds, say all possible positions are realized in different branches of an ever-splitting, universal quantum state. Every single one of these interpretations reproduces the same tested measurement probabilities. No experiment to date can tell them apart. The question of whether the electron truly has a position before measurement or truly doesn't remains open. It is a question that physics, for all its precision, has not yet settled. But here is what we can say with confidence, grounded in experiment rather than interpretation. The electron before measurement cannot be treated as an ordinary classical object, sitting at one place and following one path. The double-slit interference pattern proves this. The violation of Bell inequalities constrains how any hidden reality could work. The uncertainty principle shows that certain pairs of properties cannot simultaneously be sharp. These are not philosophical opinions. They are experimental facts. Quantum mechanics tells us where an electron may be found. It tells us the probability of finding it at each location. It tells us how those probabilities change over time and how they're affected by the electron's environment. It tells us all of this with a precision that nothing else in science can match. But it does not generally assign the electron one ordinary classical location before measurement. Whether this means the electron truly has no position, or whether it means there's a deeper level of reality that quantum mechanics doesn't capture, is a question that remains genuinely open. And I think that openness is itself profound. We're used to science giving us definitive answers. The Earth is 4.5 billion years old. Light travels at about 300,000 kilometers per second. Water is made of hydrogen and oxygen. These are settled facts. But quantum mechanics, despite being the most successful theory ever created, leaves the question of what exists between measurements honestly and openly unresolved. The theory gives you the predictions. It gives you the probabilities. It gives you the interference patterns and the uncertainty relations and the measurement outcomes. And then it stops. It draws a line and says, the rest depends on how you interpret the mathematics. Some people find this unsatisfying. They want to know the answer. They want a definitive picture of what the electron is doing when no one is looking. And that desire is perfectly reasonable. It drives physicists to search for new experiments, new theoretical insights, new ways of distinguishing between interpretations. Maybe one day someone will design an experiment that settles the question. Maybe objective collapse theories will be confirmed or ruled out. Maybe entirely new ideas will emerge that change the conversation completely. Physics is not finished. The story is still being written. But for now, what we have is remarkable enough. We have a theory that describes the behavior of every atom, every electron, every photon with breathtaking accuracy. A theory that reveals the world at its smallest scales to be fundamentally different from the classical world we experience every day. A world where probability amplitudes interfere, where the act of recording information changes what can be observed, where certain properties cannot simultaneously be precise, where the question of what exists between measurements may not have a single definitive answer. We start tonight with a simple question. Where is an electron before you measure it? And we've discovered that the answer is far stranger and far more interesting than most people expect. The electron before measurement is described by a wavefunction. That wavefunction is not a blurry picture of a tiny ball. It is a mathematical object encoding probability amplitudes for every possible position. Those amplitudes interfere. They produce patterns like the dark bands in the double-slit experiment that have no explanation in any picture where the electron follows a single hidden classical path. When you finally measure the position, you get one definite answer, selected randomly according to the Born rule. But the definite answer emerges from the measurement interaction itself, from the entanglement with a macroscopic device and the decoherence that follows. Between measurements, the electron exists in its quantum state, a state that cannot be reduced to a point on a map. It's richer than that, stranger than that, and more wonderful than that. Quantum mechanics doesn't tell you where the electron is before you look. It tells you where the electron might be found when you do look. And it tells you this with a precision that has survived every experimental challenge for a century. That is not a failure of the theory. It may be the deepest truth the theory has to teach us. The universe at its most fundamental level may not work the way our everyday intuitions expect. Objects may not always have definite positions. Reality may not always have definite properties. The world may be richer, stranger, and more open than the classical picture ever allowed. And the fact that we can understand this, that beings made of atoms governed by quantum mechanics can study quantum mechanics and grasp its implications, that might be the most remarkable thing of all. The universe built creatures that can ask where an electron is before measurement and can understand why the answer is so extraordinary. That's the mystery. It's real. It's experimentally grounded. It's still debated. And that honesty, that willingness to say we don't yet know everything, is not a weakness of physics. It's its greatest strength, because it means the story isn't over. There is more to learn, more to discover, more to wonder about. The electron is out there right now, described by its wave function, its amplitude spreading through space, ready to interfere, ready to surprise. And when you finally look, when you finally measure, you'll find it at one definite spot. But don't mistake that definite answer for the whole story. The whole story includes the amplitudes, the interference, the superposition, and the beautiful, unresolved mystery of what happens when nobody is looking. The universe keeps that secret close, and maybe, just maybe, that's what makes it worth studying. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe helps more than you know. It lets me keep making these deep explorations of the strange and wonderful universe we live in. And the next time you hear someone ask where something is, remember that at the deepest level of reality, the answer might not be as simple as pointing at a spot on a map. For electrons and atoms and photons, the question of where something is before you look may not have a single answer at all. And understanding that is one of the most extraordinary achievements of the human mind. Good night, and may you never think about the word location the same way again.